Good morning, everyone. Please recall we have ended our last discussion with this last slide. This on the last slide that we have discussed. That is the interrelationships between the different uh, different volumetric as well as gravimetric measurements. This slide will be followed by two uh, two field tests actually to measure the field density. Uh, these two will be the two field tests. One is my left hand side. This one is the field test equipment for sand replacement method, and the right side it is a core cutter method. In field, what we do, where we will at the level that is the founding level, we called it founding level, where the foundation actually be placed. At that level, we look for the in situ density or the field as it is, the density in that founding level. We are looking for that density. Along with that density, the moisture content of that particular soil at that founding level, that will combinedly indicate, or afterwards, that from those two data we can calculate the dry density. And this density, moisture content, they both actually influences the stability, the bearing capacity, the settlement aspect. Means afterwards all the geotechnical engineering properties that we are looking for, that will be guided by these two quantity, that is uh, dry density or bulk density and corresponding moisture content. So they are very important parameter, and almost all the field investigation, almost all the geotechnical structure related investigation, they do have these two quantities as a parameter. Okay, so the left hand side it is sand replacement method, right hand side it is core cutter method. I won't describe these two methods right now because it will be very difficult to describe the thing online, as the offline classes are to be started. So I will take these two in physical classes. Just the mechanism I would like to mention here. This one, the sand replacement method. See the term, it is a replacement method. So this method actually, the mechanism behind this method indicates we will determine the unknown density replacing with unknown density. Okay, the unknown density, of course, it is implying or indicating the field density at that foundation level that we are looking for. That is our unknown density, or that density has to be measured. That density will be measured in terms of our known density. That known density will come from the sand. So this method, this sand replacement method, the mechanism behind that method is our known density will replace our required unknown density. Okay. Whereas the right side method, it is the core cutter method. It will collect the in situ sample or in situ density, and the rest of the thing will be determined in laboratory. So it is a direct measurement, where the sand replacement method is an indirect measurement. Just allow me 2 minutes. Okay, so one that is the core cutter method, that is direct measurement, and the other, that is the sand replacement method, that is indirect measurement. Okay, with that, I am closing that presentation right now. The remaining one will be discussed in physical classes. So I will move into our next point or next discussion, that is index properties. Is that slide visible to you?
Yes, sir.
Fine, fine. Okay. Now the topic is index properties. What does this index property implies, or what is its requirement? It actually indicates the soil type. Okay. What kind of soil you will be encountering or you will be dealing with, and that type actually in later stage, the type of soil indicates qualitatively, at least qualitatively, the behavior of the soil under different kind of loading condition, different kind of watery condition or moisture condition. So soil properties as a whole, we can divide as index property and engineering properties. Regarding the engineering properties, what we are looking for, we are looking for permeability, we are looking for compressibility, and we are looking for the shear strength of soil. Now, what they are? Just a brief note, permeability is the movement of water, the capacity of movement of water within the soil body or within the three-phase system, that is soil, or you can say the perforated body. It is the capacity of the body, that is the soil, how is it can allow the water to percolate through its mass, right? So that is, that capacity is that called permeability. What is compressibility? How compressible or how the volume can be reduced due to application of some load or force, pressure. Okay, that indicates the compressibility of that soil. Okay, and what is shear strength? How your soil is resisting or providing the resistance against your applied shearing activity. So that is the shear strength. As simple as that. For engineering properties, we are looking for permeability, compressibility, and shear strength parameters. Whereas the index property indicates how the soil is. Okay, it is actually indicates the, or it is actually used to identify the soil as well as to classify the soil or to level the soil. What are those index properties? That index properties could be a soil grain properties, that is the individual property, individual grain property, solid property, and it could be a soil mass property or soil aggregate property, that is several of such soil particles making a soil aggregate, and property of that aggregate is called soil aggregate property. Mind it, the soil aggregate property will not be the same as the soil grain properties. As simple as your class. See, you are the soil particles. Each of you are the soil particles. So consider each of you as soil particles. You all individually do carry some properties. But thing is that when you are comes as when it is the second year's civil engineering students, then it is a aggregate property. How that 150 140 students, how they are behaving as a mass, so that is coming as soil aggregate property, whereas individual behavior of your classmates is soil grain properties, right? So what are those properties we are looking for? These are specific gravity, particle shape and size, particle size distribution, consistency limit and indices, and the fifth one is relative density or density index. The first two, that is specific gravity and particle shape and size, they are purely soil grain properties. Next, the third one, that is particle size distribution, that is soil aggregate properties. The fourth and fifth, actually, they are similar in meaning, but the fourth one is considered for cohesive soil or clayey soil, which do have some adhesive nature, and the fifth one, that is suitable for non-cohesive soil or granular soil, which do not have such adhesive nature, that is sandy soil. Okay, so fourth and fifth are qualitatively same, but they are applicable for two types of soil. fourth one is for soil cohesive soil, and fifth one for cohesion-less soil. Now, specific gravity, of course, you all know the effect of specific gravity. The more the specific gravity is, the better the soil should be, or better the soil will be with respect to compressibility, with respect to shear strength. The compressibility, see, in our case, regarding the compressibility, we will be looking for a soil which do have less compressibility. Regarding shear strength, we will be looking for a soil which do have very high shear strength. Regarding permeability, it depends on our requirement. It could be a high permeable soil, it could be a low permeable soil. Specific gravity, they do have impact on compressibility, they do have impact on shear strength, the direct impact. The more the specific gravity will be, the more should be the shear strength. The Okay, the more the specific gravity is, it is expected, it's not actually a direct measurement, but it is expected, the less will be the compressibility. The more regarding the specific gravity, it actually do not carries a direct relationship with permeability, but regarding the flow of water and some behavior regarding during that flow of water, that depends on specific gravity of soil particles. Okay. Regarding the particle shape and size, particles could be rounded, spherical shape, particles could be angular, they do have sharp edges, they do have sharp corners. Particle could be sub-rounded, that means they are not spherical, but they are angular, but their edges are not very sharp, but it is broken or it is almost rounded up, right? So they can be like that. Particles could be elongated. Elongated means its width with respect to length is very less. Particle could be flaky. That means its depth or its thickness with respect to its planar area is very small. Particle could be your needle type. Okay, there are several type of shapes that you can he will be shown physically. I will show you the particle type, rounded, sub-rounded, like that, subangular, sub-rounded, sorry. I will show them. Then comes the particle size. As we have seen in our last class, particle size with respect to clay, it goes from 4.75 up to 2 micron, that is your soil particles we can consider. Sorry, it's below 4.75, that is our soil range. Beyond that, it is gravel, it is cobble, it is boulder, all those things are coming. uh, Means higher degree, in higher consideration. Less 4.75 and less are called the soil. In between that soil, we do have sand, we do have silt, we do have clay. Clay particles mostly we consider the particle size which is less than 2 micron. Okay, from 2 micron to 75 micron, rest of the particles we called it silt, right? Beyond that, up to probably, most probably, I am not actually sure about that, boundary. From 75 micron up to most probably 2 millimeter, that called medium sand, and 2 millimeter to 4.75 millimeter, that is coarse sand. I will check that division. I will let you know correct division. So these are the particle size ranges. Of course, please remember this size is uh, equivalent diameter. Okay, what is equivalent diameter? Probably I have indicated that liquid. Is it or not? Anyhow, you just see, we do have, just suppose we do have a cube and we do have a spheroid like marble. Now think is that the volume that cube do have, with that volume if you prepare a sphere and the diameter of that sphere will be called as equivalent diameter of that cube. So any shape, any size, you consider the volume represented by a equivalent volume, the spheroid, and the corresponding diameter of that spheroid will be called the equivalent diameter. So
Sir,
either way,
the volume remains the same, sir.
yes, volume remain the same.
Okay.
Volume remain the same, and that corresponding diameter will be called the equivalent diameter of that particular irregular shape body. Right? So this is the site size concept. The size is being measured in our case. Either it could be a dry measurement, means sieve. The sieve measurement, in case of sieve, the particle or soil mass should be dried. The particles which are smaller than 75 micron, sieves are not appropriate. In that case, we go for the hydrometer analysis. In hydrometer analysis, we consider the Stokes law is valid. That part I will discuss later. During, yes. Okay, yes, sure. Just allow me 2 minutes. I'll show you.
Sir, specific gravity also.
No, specific gravity, you will find it out. Specific gravity is a very basic thing. You should know to find it out.
Sir, its function, specific gravity function, and what is it denoted as to measure
Sorry?
soil. And sorry, sir, its functions majorly. You just say specific gravity denotes soil or other
Your voice is breaking.
with respect to specific gravity.
Your voice is breaking. You can write it in your chat box.
Okay, sir.
It's a very basic definition that specific gravity do have. A standard basic definition for any solid body.
Sir, you just say specific gravity is much more than that type of soil have less compressibility, and that's the point I don't understand.
You will understand when compressibility will be taken out. Please remain your keep your patience. You will be explained. Am I visible?
Okay. Okay. Yes, sir.
Okay. Let's say I do have. Let's say this is an irregular body, or you can say a cube kind of thing, and this is a spherical body which do have same volume as this cubical body. Now, thing is that for this body, I will say its equivalent diameter is some x millimeter or x centimeter, which actually tells us the same volume that this spherical body do have. Its diameter is that equivalent diameter of that body. The volume remains same for these two body, and for this body the equivalent diameter is nothing but the diameter of that spheroid. Right? Hope it's clear now. Okay, sir. Yes, sir. Fine. Okay. Next is particle size distribution. It tells us within a soil aggregate, within a soil volume, within a soil mass. Please mute yourself, Shomojit. It tells us the proportion of different size particle, the particles having different sizes, and their proportion within a specific volume or specific mass of soil. basically specific mass of soil or aggregate, soil aggregate. So it actually gives you the distribution of different particle sizes within a soil mass, right? The fourth one is consistency limits and indices. Consistency is a degree of firmness. That means how firm is that, or how firm means here. Just you can visualize the thing. I am trying. Let's say this is your soil mass, a soil, maybe moist, maybe dry, whatever it may be. Now, how easily you can, this is your two fingers, how easily you can compress it or you can break it, that tells you the firmness, degree of firmness, okay? Or how easily you can mold it, you can give a different shape of this particular soil, that is called degree of firmness, or that is in engineering term we call it as consistency. Okay, so that consistency or that degree of firmness do have some indication with respect to water content, because the more will be the water content, the soft will be the soil body, and it will be easy to provide some shape to that particular soil body. The less the soil body, the less the water content within the soil mass, it will be very hard to crumble it, to break it, or whenever you will be trying to remold it, you will be trying to provide some shape to that particular body, it will break or it will crumble. Okay, so that uh, qualitative measurement, not in true sense the quantitative, I'll take into that part. That measurement of that indication is called the consistency indicate limits the amount of water present on that particular body, and corresponding different indices that we have derived from that limits. Limits means is the measurement of water content. It gives you there are three limits. One is liquid limit, then plastic limit, then shrinkage limit. That will be discussed one or two slides after this slide. So that is appropriate, or that is applicable to clay type of soil. Regarding the non-cohesive soil or sandy soil, that degree of firmness or that thing is represented by relative density or density index. Here, the degree of firmness represented as the density. Okay, the more the density will be, the more will be the shear strength, the less will be the compressibility, and the less will be the permeability. Okay. Now that density, relative density, indicates whether you are dense or whether you are loose with respect to the maximum and minimum possible density that you can achieve. So that is associated with non-cohesive soil. Let's have a discussion regarding the density index, or let's have a discussion on relative density first. So it is represented by your normal state or natural state with respect to the maximum and minimum possible density that you can achieve. U means here the non-cohesive soil or sandy soil. Okay, because presence of water do not have any influence in terms of providing the adhesiveness on that soil mass of non-cohesive type of soil mass. Therefore, their properties are defined with respect to their density state. So where they are with respect to the maximum and minimum density that could be possible with your given soil. So here the here the relative density is represented by dr or something. It is sometimes it is represented by r, relative rd, r suffix d. Mostly it is represented as d for density, suffixed r, that is relative. Okay, so it is used to indicate the denseness or looseness of granular non-cohesive soil. It is represented as dr, which is derived as E max minus E n, that is E natural, okay, divided by E max minus E mean. Please remember E max corresponding to your gamma or your unit weight, that is the least unit weight, and E minimum is the highest density or the greatest density, greatest unit weight that you can achieve. Okay. If you just replace that E max or E minimum, simple, this is void ratio. If you replace that void ratio with your unit weight, okay, then the expression turns like that: gamma d minus gamma d minimum whole divided by gamma d max minus gamma d minimum. This whole component will be multiplied by gamma d max minus gamma d. Just replace this gamma d max with gamma d. See, gamma d max corresponds to gamma d minimum. Gamma d, excuse me, sorry. E max corresponds to gamma d minimum. E minimum corresponds to gamma d maximum. So the minimum void ratio indicates maximum density. So if you have the Emax and Emin, as well as if you have your natural density or natural void ratio in field, then you can conclude how dense you are with respect to your that movement zone. That is the movement zone, that Emax or E minimum. That is so that you can have the thing. Yes, Sravnik.
Hello, sir. In how to achieve Emax and E minimum?
Yes. You are muted. You please unmute yourself.
Hello, sir. Am I audible?
Yes.
Sir, in field, how to achieve Emax and E minimum?
Yes. See, in field, of course, you are having E natural, right? You just
Yes,
make
sir.
either core cutter method, or you can perform the sand replacement method. From there, you can have gamma field, gamma natural or E natural. Okay. Now take that soil, take that non-cohesive soil in lab. In lab, you will have a vibration table. Okay. In that vibrating table with specific codal reference, you can determine the E minimum, that is the gamma D max. Okay. And simultaneously, you can also perform a test which will give you the gamma D or gamma minimum, that is E max. So that E max and E minimum you have to determine from laboratory testing.
Okay, sir.
Okay. That is a laboratory test actually. Okay. Now, this relative density, of course, you can find it here. The void ratio is associated with it, and that void ratio is nothing but the degree of packing, or the how you are, okay, in field how it is achieved, right? Your question was in field how it is being achieved. In field, this increase in density or decrease in void ratio can be achieved with compactors, the compaction machines, that is roller in most of the cases. Okay, that roller can be of different time based on the soil type. If you have sandy soil, then a different kind of roller will be used. If you have a clay soil, then different kind of roller will be used. This different kind is depending on the roller foots, the rolling drum. They are having different type of arrangement. If you have a clay type soil, then you will have ship foot kind of roller. That ship foot kind of roller means that drum through which you will be rolling the surface, the drum will be having some uh, protrusion like our shoe grips. Okay, so that kind of protrusion will be used in case of your clay type of soil, where if you want to compact, if you want to roll some sandy soil, then the vibration technique, that means the roller drum will have a vibrator inside, and entire the rolling system will be accompanied with mass as well as vibration. So that is a vibrating kind of roller, which is mostly applicable in case of your um, sandy soil. You must have seen some road roller, or the rolling system which we use to compact our cricket, this, what is that, pitch, right? So these are the roller or compactor that will be used to roll or to compact our field, that is soil, to increase the density or to decrease the void ratio. And the degree of compaction or increase in density, that can be controlled. Okay, those things will be discussed in your compaction compaction chapter. Probably that will be dealt with. That will be probably Narayan. Narayan will consider that part. Anyhow, it is nothing but how compact or how your particle arrangement is there within that soil mass. The more the compaction stage, the more the particles are close to each other. That actually gives you that indication that the void ratio is decreasing or the density is increasing, right? Now thing is that it is not only depending on the grain size, but it is also depending on grain shape. If you are having the angular shape kind of, the sharp edge, the angular shape, the plane surface, that kind of grain shapes, then you can expect. I am saying it is expectation only. It is only the expectation. It may deviate from your expectation depending on grain size. If it is a elongated, if it is a flaky type of soil or grain, then this expectation will not be valid. Anyhow, if it is a standard grain, I am considering the grain is well shaped, well sized, then the shape, that means whether it is angular or rounded, that actually gives you the packing property. If you have a rounded shape, then packing will not be that great. But if you have a angular shape of grains, then packing will be more. You can expect a higher density, lesser void ratio. Okay. Now, nature of grain size distribution curve. That means if, okay, leave the nature, grain size distribution within the soil mass. If you have a well proportioned grains size, regarding the size, if you have all kind of grain sizes within your soil body, then you can expect, you can reach a higher density or you can achieve a lesser void ratio. As compared to, if you just consider, if you are having a similar type of grain sizes, then the compactness will not be great, because in case of similar size aggregates, the in between void spaces will be much higher. Instead, if you have a grain size, large grain size, then a smaller grain size, then the void space or empty space between the two bigger elements, bigger particles, will be occupied by smaller particles. That will increase the density, that will decrease the void ratios, right? And the last one is fine contents, that is the part of the soil whose size is less than 75 micron or 0.075 millimeter. Here, researcher has developed this curve which indicates the effect of fine contents. Hmm. It's not that always if you have higher fine contents, you can achieve greater density or you can achieve lesser void ratio. People have seen, if this is your curve corresponding to maximum void ratio and this is the curve corresponding to minimum void ratio, people have seen if you have around 35 to 40% fine content within the soil mass, then you can achieve the maximum density or minimum void ratios. See, these are the two your parallel lines. So what they have done, they have taken some soil, they have mixed fines with respect to percent of your soil mass, and they conduct a similar test to achieve E maximum or E minimum. What they have found, they have come up with these two curves. This one corresponding to E max or minimum density. This one corresponds to E minimum or maximum density. You can see around 35 to 40%, not even 40%, less than 45 40%. If you have the fine content, then you can achieve the maximum density or minimum void ratio. So this is an experimental fact that indicates the effect of fine contents. In case of our engineering judgment, if you found the relative density as 0 to 15%, see this 0 to 15% means with respect to your maximum range where you are. Okay, if you have 0 to 15% relative density, then the soil or deposit, non-cohesive soil deposit, will be called very loose. If you have 15 to 50% relative density, then it will be called as loose. If you have 50 to 70%, it will be called as medium dense. Up to 80% from the medium dense, it will be called dense, and beyond 85%, it is very dense. Practically, even if you are conducting the similar experiment in labs, beyond 90% or even beyond 85% sometimes, making the soil dense is very difficult. When the compaction chapter will be dealt, probably this topic will be discussed regarding the compaction effort. It is not that you are rolling that particular surface, rolling and rolling and rolling. You are expecting you will be achieving greater density. It won't happen. But after some time, after some rolling, after some compaction effort, you can you can expect your this density regarding achievement. That means increasing density can be a reversal, can have a reversal. That means after some compaction level, the density will be decreasing mode. Why it is, that will be dealt with compaction chapter, but just take the note. This reversal is due to the dilatancy phenomena, due to the what is that, reflection of compaction effort, reflection of energy that is being supplied to that soil body. That reflection actually causes the dilatancy phenomena. I will discuss the dilatancy, and that makes the soil the reversal phenomena. That is, the soil will be loosen. Okay. So this is about the relative density concept applicable to non-cohesive soil or sandy soil, right? Next, the index property, which is applicable for clay soil, that we call consistency limits. It is described as the degree of firmness of a soil in a qualitative manner. Okay, it is not actually quantitative manner. We have some measurement which will convert it or which have bounded this qualitative definition. They have segregated this qualitative term like very soft, medium, stiff or hard. So these are the qualitative term associated with degree of firmness of clay soil. That is very soft soil, very soft clay, then soft clay, then medium stiff clay, then stiff or hard clay. Regarding the firmness, just imagine you have soil in your hand. If it is very soft, then you can put any shape on that soil. But thing is that that shape may not be may not hold good for a very long time. It will collapse because it is very soft. The water portion on that particular soil is very high amount, so it cannot withstand the self weight even. Okay, then comes the soft portion, You can mold the subsoil in any shape. Okay. Afterwards, it is medium stiff up to a level of molding energy or molding work. It will keep your intactness, but beyond that, it will crumble or it will break down. Then comes the stiff or hard soil, which is very difficult to provide any such molding effect, molding work. Okay. So it is described as the degree of firmness of soil in a qualitative manner, which is very soft. This qualitative manner, it indicates very soft, indicated by very soft, medium stiff, and stiff or hard soil. Or in other way, how it can be defined, it actually indicates the ease with which a soil can be deformed. That is nothing but the molding effect. It indicates the ease with which a soil can be deformed. Okay. The entire thing is depends on amount of water present on the soil body. The more water will be, the more ease to deform the soil. Okay. The more water will be, the less stability of the soil as well. Fine. It has been identified, this phenomena, this movement or this change in hardness or firmness from very soft to stiff, this has been identified by Atterbuck, who was a Swedish soil scientist in around 1911. Okay, and this person has indicated the boundary or limiting water content in a soil body, which will show the change in phases or change in state within the soil body. Okay. So Atterbuck, the limits he has indicated is called Atterbuck limits, or this limits nothing but water content. Okay. Atterbuck limits, or sometimes it is also called consistency limits. It actually indicates the boundary level of water content at which the soil undergoes a change from one state to another. Here, the state means the degree of firmness, that is soft, medium, stiff, or hard, like that. What are those limits? Those limits are liquid, or those states are liquid state, plastic state, semi-solid state, and solid state. In between liquid state and plastic state, the limiting water content is called liquid limit. It is expressed as LL, which is nothing but WL in percentage. See, this WL means W means water content, L means liquid limit. So this WL means water content, percentage of water content at liquid limit. Okay. In between the plastic state and semi-solid state, the limiting water content is called plastic limit and represented as PL, which is nothing but the water content, which is WP in percent. In between the semi-solid and solid state, it is the shrinkage limit indicated as SL, and WS, that is the water content corresponding to shrinkage limit. Difference between the liquid limit and plastic limit water content is index is indicating some property, or it is the index, it is showing some value, that value called the plasticity index. One thing you remember, from A to C, or okay, from liquid limit to shrinkage limit, the soil body remains at its saturated state. That means all the white spaces are being occupied by water. Okay, so the states are liquid state, plastic state, semi-solid state, and solid state. And limits are liquid limit, plastic limit, shrinkage limit. Okay. Now, what is the property of this limit, or what is the behavior the limits do have? In liquid limit, it is actually the maximum water content at which the soil water mix acts as suspension and shows practically no resistance to flow, virtually no shear strength. What does it mean? Okay, what does it indicates? Probably I am visible to you. See, this is a water bottle. It contains water, right? Now, if I just put a teaspoon of soil here and just stir it, it will become a suspension of clay, clay in water. That is a suspension. But still, thing is that when the clay was not there, this water body won't take any shear strength. Okay, because the water do not have any shear strength, so it won't take any shear strength, shear stress. Now, when you are putting some soil here, until it remains as suspension, it won't take any shear stress or it won't resist any shear activities. Like you have put 1 teaspoon of soil there, it will behave like a liquid only. Put some another few spoons of soil. What you will find, this suspension will become a bit, what is that called? It will increase its density. What is called it?
Sticky.
কি বলে? No, no. গাঢ় ইংরাজি কি গো? আমি কি ভুলে যাচ্ছি কেন?
Dense.
Dense.
Viscous.
Dense. Viscous kind of thing. Yes. It will become.
Slurry.
It will give. Yes, yes. Probal.
Slurry.
Huh?
SLURRY.
Slurry.
SLURRY. Slurry.
Yeah, it is of course a slurry kind of thing, but it will increase its density. It will increase the viscosity, and gradually you will find if you just put a this straw. This is a straw. If you just put a straw, it will remain straight for some seconds, some moments. Okay. Now, at that boundary level, when that slurry or that suspension of soil and water will provide you some sort of shear strength. That means when you put this straw inside that bottle and the straw remain at straight position or remain or holding its position straight, that means that slurry, that suspension is providing some sort of shear resistance against its self weight, right? If this water, if I am putting that one in that water and it do have some mass, it do have some weight, due to its self weight, it will just tilt it. That means that self weight is not being resisted by that viscosity or by that shear strength of that particular liquid. But when you are increasing its density, the slurry gets dense and dense and dense. A limiting stage will come. State will come when this straw will be just given some sort of resistance against its that tilting by that particular slurry, right? That moment when that particular system soil water mix is started to provide some sort of shearing strength, shearing resistance, that is called the liquid limit water content. Okay, so that is the limiting water content where the soil water mix, that is the maximum water content you can say, where the soil water mix will provide you some sort of shearing resistance or shear strength. Okay, practically what we do consider, we consider if that soil water mix, it has started to provide you a shearing resistance around 2 to 3 kilopascal kPa. That moment we consider it has reached that ideal condition when it has started to provide you some shear strength, shearing resistance. So that point of time, that water content is called the liquid limit. Got it?
Yes, sir.
Okay.
Liquid limit means the between the liquid and the plastic state. Yeah.
Liquid limit means the transition or maximum water content to reach the liquid state, or it is the limiting water content between liquid and plastic state. Yes, you are right.
Okay.
For every practical purpose, as I was mentioning, a water content when the soil water mix shows a shear strength about 2 to 3 kilopascal, considered as liquid limit. Okay. Now plastic limit, if the water content, now okay, I am keeping my video on, that will be easier to you. Okay. Okay. Now this body, this is a mix which have achieved 2 to 3 kilopascal of shear resistance or shear strength. Now what the plastic limit is mentioning, if the water content gradually reduced, a state comes when it just begin to crumble. Okay. Now what you can do, you can extract the water here. Now that it is a soil water mix, and what you are doing, you are extracting the water from that particular body, not the soil particle. See, this is very ideal thing. If I am saying the extracting, you will find, okay, I am just sucking the water from that mixing with the straw. It is not like that. This extraction means the evaporation. Okay, evaporation in normal temperature. Now, if you are extracting the water from there, what will happen? This entire volume will be reducing. Okay. Thing is that here, what you have excess water than the minimum void spaces within the soil particle, if the soil particles are, all the soil particles are in contact with each other. In that case, whatever the void spaces will be, now here in case of liquid state or liquid limit case, we have excess water. In that condition, if you are starting to if you are extracting the water, what will happen? The entire volume will reduce, but the reduction in volume will be due to the reduction in water volume only. Okay. So you are reducing the water, you are reducing the entire volume of that particular soil body, but you are not extracting any of the soil particles. So whatever the volume reduction is, that reduction is taking place due to the volume reduction of water only. Now, if that is true, then what you can say, the soil water mix remains saturated. Right? Because what I am doing, I am just extracting the water, I am not extracting the soil body or solid particles. And which water I am extracting? The water which was in excess of its minimum water or minimum void space. Okay, that amount of water I am extracting from that body. So whatever the water due to the reduction in water content only. So volume change will be equal to, means total volume change will be equal to the volume change of water. Okay. Now you are reducing, you are extracting the water, you are extracting the water. A stage will come when the particles will be close to one another, if they will be in touch with one another, and their void spaces or their particle arrangement will be fixed, will be locked, right? Beyond that, if you try to extract the water, what will happen? The void spaces which were filled with water, now water will be extracted from the void spaces, and the soil will not be saturated anymore, because now the water content as compared to the total void space is less. Okay, now the soil has become unsaturated zone. Fine. So this is how.
Sir,
Well,
sir, void space with which respect? মানে স্যার কোন সয়েলের রেসপেক্টে void space বলছেন?
কোন সয়েল বলতে?
Sandy
স্যার
soil.
আপনি
Or yeah.
আপনি প্রথমে জল নিলেন।
It is clay. It is not valid for sandy soil. It is a clay soil.
স্যার আপনি প্রথমে জল নিলেন, তারপর জলে অ্যাড করলেন সয়েলটা, তো
বেসিক্যালি
ওটা
আমি
তো সয়েল।
জল নিয়েছি ঠিকই, আমি শুরু করলাম জল থেকে, কিন্তু অ্যাকচুয়ালি আমি সয়েলের সঙ্গে জল মেশাই, নট জলের সঙ্গে সয়েল।
ও ওকে স্যার, ওকে স্যার।
অ্যাকচুয়ালি
তো ওটা ন্যাচারাল যেটা void ratio।
হ্যাঁ, এখানে আমার কাছে ছিল জলের বোতলটা, তাই আমি জাস্ট বোঝানোর চেষ্টা করছিলাম। অ্যাকচুয়ালি it's a its basic constituent is soil. I am mixing the water. ঠিক আছে? So your
Yes,
soil
sir.
amount or soil solid is fixed. You are mixing the water. A state will come. It won't behave like a solid body, but it will behave a liquid body. So that limit will be called the liquid state or liquid limit. Now you are from that liquid limit. You just imagine the soil solid is fixed. You are extracting the water, right? So whatever the volume reduction will take place, that volume reduction will take place due to the water volume only, and by that way the soil remains saturated with that remaining water content. Now you are extracting. What will be the situation at some stage? What will happen? The soil mass, whatever the particles are within that soil mass, they will be close to each other, and they will be they will be in touch with one another. So what will happen? Their particle arrangement will be locked. They will have a fixed arrangement, and due to that fixed arrangement, their void spaces in between the particles will be fixed, right? Now, as the void spaces within the particles gets fixed, then from that fixing point or fixing structure, fixing water content, or fixing fixed void, again if you try to extract the water, what will be the situation? The void spaces will no longer be saturated with the remaining water content. The soil becomes unsaturated. Okay. So now what is there? আমার স্লাইড কি দেখা যাচ্ছে? Okay. Now the plastic limit, it indicates it actually implies if the water content gradually reduced, a state comes when it just begin to crumble. That means when your shearing activity, that means when you are trying to remold that one, you are trying to make some, if you are trying to make some thread on that moist soil, at some stage it will start to crumble, or it will start to provide you the cracks, it will break down. So that is the point, that is called the plastic limit. Okay, plastic limit water content. Now in between liquid limit and plastic limit, you can work with soil water mix without any cracking, without any crumbling. Okay, now from that plastic limit water content, if you started to extract the water from that saturated soil water mix, saturated water soil body, if you started to extract the water, what will happen? The water now will exert some dragging action along with its extraction. That means, how I can make you understand the thing, it's kind of suction effect. Let's say this is a soil particle, and this is a water molecule or water particle. Okay, water molecule. Now this is the close contact when it was saturated. What will happen if I am trying to detach or if I am trying to extract that water molecule from that solid particle? It will exert some dragging action. It will exert some suction. This is due to surface tension. It will take that soil particle, or it will force the soil arrangement, particle arrangement, to some extent, so that the particles, what was their initial arrangement, it is initial closest arrangement, the soil particles now rearrange themselves to some extent. Okay, now that rearrangement actually creates some scope of reduction of total volume. Mind it, scope of reduction of total soil volume, okay, which is not equal to the extracted water volume. Okay, I am repeating. Up to the plastic limit, your extracted water volume is equal to your total reduction in volume. Okay. Beyond plastic limit, due to that suction effect, due to that dragging effect of that water extraction, your extracted water volume will not be the same to that reduced soil volume. Okay, because of particle rearrangement and rearrangement in void ratio. But still, due to that particle rearrangement, due to that change in void ratio, your soil mass, soil body remains saturated. But the thing is that the linearity relationship, that is the volume, water volume equal to reduction in water volume equal to reduction in total mass, that linear relationship will not exist anymore. But thing is that there will be some non-linearity will be associated with the behavior, associated with that reduction phenomena. Still, the soil remain saturated. Okay. Now, even that procedure, when again you are extracting the water, what will happen? The particle rearrangement will cease. So they won't rearrange themselves anymore, though maybe the suction pressure will be higher. But thing is that the working, the energy that has to be developed there to rearrange the particle further will not be the sufficient, that suction pressure will not be sufficient to rearrange that particle arrangement, particle interlocking position further. So the water volume will be extracted, the water volume will be reduced, but there will not be any effect on total soil volume. The total soil volume will remain the same, but gradually we will have reduction in water content without having any effect on the soil volume. Okay. So these are the states. Now this state, when from the plastic stage to that non-linearity portion up to where you have the fixed volume, that non-linear portion is called shrinkage or semi-solid state. Beyond that, that means where you don't have any volume change but you can extract the water, that is called solid state. Okay. In between plastic state to semi-solid state, the limit is called plastic limit. In between the semi-solid state to solid state, the water content called shrinkage limit. So up to shrinkage limit, your entire soil water system is saturated. Right? It will take some time. You please read your textbook. It will take some time, 1 or 2 days, to understand the phenomena. I can repeat the thing, but thing is that you please read the book or think at least yourself. Okay. Now, what is shrinkage limit? a further reduction in water content results in a less volume decrease than the reduction of soil volume. Water volume. That means the whole volume reduction is not equal to the volume extracted, water volume extracted from the system. Okay. A stage comes when no volume change occurs with reduction in moisture content, and that is called the shrinkage limit. Okay. Fine. For every practical purpose, up to shrinkage limit, the soil is considered to be saturated. Now here a schematic presentation is given where you have some state which is represented state, then this is that states which is liquid, plastic, semi-solid and solid, and this is given you the water content, and this is the consistency along that state, this is saturation situation along the state, and this is the volume. Let's gradually think about this. In liquid stage, you have the water content, excess water content, and in that state, you don't have any shearing strength, and the system soil water mix is almost behaving like a liquid, having the saturated 100%. Okay. Now you gradually reducing your water content. This is the boundary water content. When you are providing, you are getting some, you are being provided with some shearing strength. So that is the liquid limit water content. You are still in saturated zone and the volume is decreasing. Now there is a plastic zone in the soil and you have some limiting water content beyond which it is semi-solid. So again, this plastic zone, the consistency will be very soft to stiff. Okay, the soil will be very soft, and at that limit, that plastic limit, soil can behave as stiff soil. Still, the soil is remain saturated and volume is decreasing, and that decrease is, and the slope angle is 45 degree. If you draw which is volume versus total volume versus water volume, extracted water volume, it will provide a linear relationship, straight line, and the straight line will be 45 degree to any of the axis. Now beyond that, when you are reducing your water content, the linearity behavior will no longer exist, but there will be some non-linear behavior, there will be some curvature, curvy nature. But thing is that the soil is again saturated up to that limit, beyond which if you extract the water, there will not be any reduction in total volume. And the soil, regarding the consistency, from the semi-solid, it is very stiff. It can go up to very hard, like rocky strata. Okay. So here you have in that limit, the semi-solid limit, you have the saturation point as 100%, and it can be up to 0%. That means you can dry it up the entire soil water mass, and it will be just a lump of solid. Okay. Beyond that point, beyond the shrinkage limit, it is just constant volume. So this is a schematic presentation. It will be even clear with that diagram. See here the soil water mix. Can you see the slide 6?
Yes, sir.
Yes, sir.
Okay. See here. This is a soil water mix. You have the soil grains. This is your soil grains. The particles are not interconnected, but the particles, that interconnection portion or that in between two particles, you have water body. And as water do not have any shearing resistance or shear strength, so any shearing application, shear force application of shear force, the water won't resist that shear force, and the entire soil water mass will behave as liquid. Okay, so this is your liquid, and of course it is a saturated body. So this, beyond that limit, it is your this is your liquid state. Okay, so it is the soil water mix will behave as liquid. Now when you are extracting water, so this is in water volume. Of course, similar amount of your total volume is reduced. Some of the particles get touched with each other. This is one touching point. This is another touching point. This is almost a touching point. So here in this situation, the soil is offering some sort of shearing resistance. So this is that gray zone. These two lines is indicating that zone when the soil has started to offer you some sort of shearing resistance. Practically, this second line, that is corresponding to 2 to 3 kPa kilopascal, that can measure actually, that is your liquid limit. So this is your liquid limit water content soil water mix situation schematically, where you can expect some sort of shearing resistance the soil will provide. Now you are extracting the water, the similar amount of your uh, water volume and reducing. So the relationship is linear, and that is 45 degree to each of that. What is that? Axis. Now, what is happening? Particles are getting close to, together. They are plane contact, and they are providing higher shearing resistance as you are extracting, as you have extracted the water. Okay. So up to that point, you have extracted the water, and this is your plastic limit situation, where almost all the soil particles are in touch with each other, right? Beyond that, when you will be trying to extract the water will give you some sort of suction effect or dragging effect, that is due to the surface tension. And for that, this particle arrangement will be slightly changed. This change means the particle shapes, or this arrangement is somewhat distorted. Okay, but the soil remains saturated with its existing or modified uh, void spaces. Okay, and thing is that the amount of water that you have extracted will not be the same as the amount of void space, amount of total volume reduced. See, it is a total volume now, which is up to that point approximately, but amount of water is this much. So here the linearity relationship will not exist, but there will be some non-linear relationship. Therefore, it is highlighted. So there you have the concave upward type of behavior. So this point to that point, and okay, beyond that, if you have extracted the water, what will happen? The void spaces in between the soil particles, they will remain unsaturated. They won't be fulfilled with water, and the water body gets unsaturated, and this entire structure soil arrangement is getting fixed. So there will be no volume change. So from that point beyond, that is that point, you won't have any volume change, but the entire volume will remain constant up to making the water content zero. That means completely dried. So this is the relationship between the total volume and water content. Just a few minutes, allow me. Hello. সরি ফর দ্য ইন্টারাপশন। তোমাদের 11টা থেকে ক্লাস আছে না? So I'll be having. Okay. So this is the relationship between the total volume change and water volume change due to the extraction of water or change in water content. So up to the plastic limit, the behavior is linear. Whatever the volume change, total volume change, that is the water content, reduction in water content. Beyond the plastic limit, up to shrinkage limit, the behavior is non-linear. Beyond the shrinkage limit, the volume gets, the total volume or the soil volume gets constant up to making the water content as 0. That is completely dry situation, dry soil. Okay. Now this one is presenting you the stress strain behavior at different state. Okay. So what you have here, a liquid limit. This is liquid limit, and beyond that liquid limit, it is liquid state. In between liquid to plastic limit, it is plastic state. In between plastic limit to shrinkage limit, it is semi-solid state. And beyond the shrinkage limit up to 0 water content, it is called solid state. Okay. At around liquid state or liquid limit, or just lesser to that liquid limit water content, the stress strain behavior, is represented with the first curve. Here you can just see the blue line. It actually indicates the stress strain behavior of that soil. Okay, this soil. So it's behaving almost like a liquid. That means when you are providing some sort of deformation or strain, it almost giving nothing to you. It is parallel or it is almost merging to that x-axis. If you are reducing the water content around plastic limit or semi-solid limit, the shearing resistance is more. You will be getting some prominent stress strain behavior like that blue line. And when you are again reducing the water content, this stress strain curve will show higher property, higher range. Now when you are having some semi-solid or even solid stage, you might have a soil clumping or breaking. When you will be trying to break that constant volume, you will be having some breakage. The molding means you are applying some shearing effect. You are applying some shearing force. So you can expect, if it is a very steep, you can expect the peak also here. Okay, the peak, that means it is going up, then it is having the peak, and then it is collapsing or it is failing. So these figures actually showing the development of stress strain curve starting from liquid phase to solid phase. This actually indicates how soil is offering you the shearing resistance. Okay. So here some indices based on the liquid limit, plastic limit, and shrinkage limit is given. I would request you to remember these things. They are very helpful in indicating the nature of soil, in classifying the soil. I'll explain all those indices in the next class. Okay. For the moment, I'm stopping here. Thank you for attending the classes. Probably we will meet in physical classes from the next week or whatsoever. But if required, I'll ask for some additional class online. I hope you will allow me to take some classes like that. Will there be any problem if I take some additional classes?
No, sir.
No, sir.
Okay, fine.
No, sir.
Okay, thank you. That's all for today. You please mention your roll number in the chat box so that I can take the attendance. Thank you.
for the session.
You can leave. You please attend your next class by the time I take the attendance.
Sir, will you send this PDF or did you already have?
I'll discuss that part later.
Okay, sir.
Okay.